Hi, this is Dr. D. Amsaveni, Associate Professor, PG and Research Department of Mathematics, Sri Sharada College for Women, Salem. In this video, we will learn about Laplace transform and properties of Laplace transform. Laplace transform is named in honor of the great French mathematician Pierre Simon de Laplace, who first introduced it in the 18th century. The Laplace transform is an integral transform that plays a crucial role in mathematics, physics, and engineering. Like all the transformations, the Laplace transform changes one signal into another according to some fixed set of rules and or equations. This transformation is useful for solving differential equations, integral equations, and other type of equations that describe complex systems. The best way to convert differential equations into algebraic equations is the use of Laplace transformation. So this is a fundamental mathematical method widely used in the fields of engineering, particularly in electrical engineering, control systems, and signal processing. So in this video, we will discuss the definition of Laplace transform and finding Laplace transform of various functions, linearity property and shifting property of Laplace transform, change of scale property in Laplace transform, Laplace transform of derivative, and Laplace transform of integrals and multiplication of t. First, let us see the definition of Laplace transform. Let f of t be a real valued function of the variable t defined for all t greater than or equal to 0. Then the improper integral 0 to infinity e power minus st f of t dt is defined as the Laplace transform of f of t if this integral exists. Improper integral means if the integral has infinite values, that is, the integral has an infinite upper limit or lower limit. Here we have the upper limit as infinity, so this is improper integral. So if the improper integral exists, we can define the Laplace transform of f of t. So this integral is a function of parameter s. So where the parameter s is real and f of t is denoted by the symbol f bar of s or L of f of t. That is, L of f of t is equal to f bar of s is equal to integral 0 to infinity e power minus st f of t into dt. So this is the definition for Laplace transform. Next, we see the Laplace transformation of various functions. First, let us see Laplace transform of the constant one. So, by the definition, L of f of t is equal to del 0 to infinity e power minus st into f of t dt. In this definition, we replace f of t by 1 because we are finding the Laplace transformation of 1. So we replace f of t by 1 in the definition. So L of 1 is equal to integral 0 to infinity e power minus st into 1 dt. So this is e power minus st dt, and we know the formula, integration formula, integral e power ax is equal to e power ax by a. So here the variable integration with respect to x, the coefficient of x is a. So when we integrate this function, so the coefficient of a should be in the denominator. So like this, e power minus st, we are integrating with respect to t. So e power minus st by minus s. Here the variable is t and the coefficient of t is minus s. That should be in the denominator. That is e power minus st by minus s, and the limits are we have here 0 from 0 to infinity. Now we apply the upper limit and lower limit in this function. So e power minus s into infinity, because we are Substituting the limits for t. So e power minus infinity by minus s, and then lower limit e power 0 by minus s. And we know that e power minus infinity is equal to infinity. And then e power minus infinity can be written as 1 by e power minus infinity. Now 1 by e power minus infinity, already we know that it is infinity. So 1 by infinity is 0. And e power 0 is equal to 0. And here this is 0. 0 by anything is 0. And then minus, we get minus e power 0 is 1, 1 by minus s, and then this minus will get cancelled, we get 1 by s. So 1 by s if this is, yeah, this s greater than 0. So L of 1 is equal to 1 by s if s greater than 0. So likewise L of 2 we can find this. L of 2 is L of 2. The Laplace transformation of 2 is 2 by s, and L of 3 is 3 by s, and then and so on. Next, the Laplace transformation of t. L of t is equal to 1 by s squared if s greater than 0. By the definition, L of f of t is equal to integral 0 to infinity e power minus st into f of t dt. And f of t is here t. We are finding the Laplace transformation of t. So f of t is replaced by t here. And then L of t is equal to integral 0 to infinity e power minus st dt into dt. Then here the integral is the product of two functions. So we are using the integration by parts, that is integral u dv is equal to uv minus integral p du. So for this, let us take u is equal to t, and dv is equal to e power minus st into dt. And this should be differentiated. So du is equal to dt we are getting, and this should be integrated. Then only we are getting v. Integral dv is equal to integral e power st dt, and b is equal to e power minus st by s. Here the integral and differentiation will be cancelled, so we are getting v, and v is equal to, when we integrating this one, e power minus st by s we have got. So therefore all the things we have here, so u, v, and du, dx, uh, and then we are going to substitute in this formula. It is equal to u is t, v is e power minus st by s. The limits are 0 to infinity minus integral 0 to infinity v is e power minus st by minus s into dt. If we apply the upper limit and lower limit for this term, so we are getting 0, and then this minus and this minus will be plus, and then integral 0 to infinity e power minus st dt. And then 1 by s can be taken outside, integral 0 to infinity e power minus s into dt. So integrating e power minus st with respect to t, and then e power minus st by minus s, limits from 0 to infinity, and then we apply the limits, upper limit infinity, then e power minus infinity is 0. When we apply the lower limit, it will be 0. So 0 by minus, so we get like this, e power e power minus infinity by minus s minus e power 0 by minus s. So this is 1, and this will become 0. So minus 1 by minus s, then 1 by s. So 1 by s already is here. So 1 by s into 1 by s, 1 by s squared if s greater than 0. Similarly, we can find the Laplace transformation of t, that is 2 by s cube. So here in the definition, so we replace f f of t is equal to t squared. So L of t squared is equal to there 0 to infinity e power minus st into t squared dt. And we take u is equal to t squared and dv is equal to e power minus st dt, and differentiating the function u with respect to t, we get 2t into dt, and integrating this function, so we get v is equal to e power minus st by minus s. So again using the integration by parts, so and in this formula we substituting all those things. So after substituting, and then we get like this. So this will be 0 again when we substitute upper limit and lower limit. And then here we are getting this function. So minus minus will get cancelled. So minus in this yes can be taken. This 2 and yes, this 2 and yes can be taken outside. So 2 by s into integral 0 to infinity e power minus st into dt t into dt. This integration already we have seen in the previous one. So that is integral integral 0 to infinity e power minus st into dt, that is 1 by s square. So now we are substituting this e power 1 by s square for this integration. Integral integral 0 to infinity e power minus st into dt, that is 1 by s square. So 2 by s into 1 by s square, which is equal to 2 by s cube if s greater than 0. Similarly, we can find L of t cube is equal to 2 by s power 4. In general, L of t power n is equal to n factorial by s power n plus 1, where n is a positive integer. The next Laplace transformation of e power minus at, that is 1 by s plus a, if s greater than minus a. So let us see how to integrate this function, and how to find the Laplace transformation of this e power minus at. Again by definition, L of f of t is equal to integral 0 to infinity e power minus st f of t dt. Here f of t is e power minus at, is substitute in this formula. L of e power minus at is equal to integral 0 to infinity e power minus st t e power minus at into dt. And then so this already we have studied in lower classes, that is a power m into a power n is equal to a power m plus n. So by using this we can write e power minus st minus at, uh, and then we take here e power minus t outside, and then we get e power t minus t into s plus e dt. So when we integrate this function, so e power minus t, like integral e power ax by a, sorry, uh, e power dx is equal to e power ax by a. So like this, say the coefficient of t is s plus a. So we are integrating with respect to t. Say e power minus t into s plus a divided by minus s plus a. So this s plus a, the coefficient of t will be in the denominator. So when we integrating, and the limits from 0 to infinity. So again, we are applying the limits e power upper limit for t, that is e power minus infinity by minus s plus a, e power minus infinity by minus s plus a, and then when we apply the lower limit will be e power 0 by minus s plus a. So we know that this is 0 and this is 1. So we get minus 1 by minus of s plus a. So this will be plus 1 by s plus a if s greater than. Similarly, we can find the Laplace transformation of e power at. So L of f of t is equal to, by the definition, integral 0 to infinity e power minus st into f of t dt. Replace f of t is equal to e power at here. Then L of e power at is equal to integral 0 to infinity e power minus st f of t is e power at dt. Here we write by using the property a power m into a power n is equal to a power m plus n. The powers can be added here. that is e power minus st plus at. And then in this, we are taking minus t outside. So when we take minus t, it will be plus s minus a. Then we have like this, and then integrating this function with respect to t, then e power minus s t into s minus a by minus s minus a, because the coefficient of t in the exponential is minus s minus a. So that should be in the denominator. So and then apply the limits. Here we apply the limits e power minus infinity by minus s minus a minus e power 0. This is a lower limit. So minus s minus a. And this term will be 0. Then minus minus will get cancelled. And the e power 0 is 1. So 1 by s minus a. So this is if s greater than a. So L of e power minus at is equal to 1 by s plus a, and L of e power at is equal to 1 by s minus a. Next, we find the Laplace transformation of sin at, that is L of sin at is equal to a by s squared plus a squared if s greater than 0. Let's see how to find the Laplace transformation of sin at. So by the definition, L of f of t is equal to integral 0 to infinity e power minus st f of t dt. So replace f of t by sin at. So integral 0 to infinity e power minus st into sin at dt. And we are going to use this formula, integral e power ax sin bx into dx is equal to e power ax by a square plus b squared a into sin bx minus b into cos x. This is the product of exponential and trigonometric function, product of two functions here. So we can solve by using this formula. And then here this a is the coefficient of a x in the exponential function, and this b is the coefficient of x in the sine function. So compare these functions and this one, this one, and we can write a is equal to we have a is equal to minus s, because a is the coefficient of x in the exponential function. Here we have the variable t, here we have the variable x. So compare this, and we have a is equal to minus s. And what is our b? It is the coefficient of x in the sine function. Here coefficient of t in the sine function, that is b. So b is equal to a. And the variable is here x, and here t. So replay, we are going to substitute all those things in the formula here. So we get e power minus st, e power minus st, because a is minus st, yes, x is t. So minus s into t divided by a is minus s. So minus s the whole square is, again we get s square, plus b is a, so a square into this is minus s, and this is a, then a replaced, and the x is also t we replace. So minus s sin bx sin at minus a into cos at 0 to infinity. So apply the limits, upper limit infinity. If we substitute, then it will become 0. So 0 minus lower limit 0, if we substitute e power 0 we will get, and then in the denominator it is a square plus a square. So what about this thing? So if we substitute t is equal to 0, sine 0, sine it is sine 0. So sine 0 is 0, sine 0 is equal to 0, cos 0 is 1. So sine 0 is 0 into minus s is 0. So 0 minus a into cos 0 is 1. So we get like this. So and then e power minus 1 by 1 by s squared plus a squared, here minus a. This minus will be plus, then a by s squared plus a squared if x greater than 0. So this is the Laplace transformation of the function sin at. Similarly, we can find the Laplace transformation of cos at. cos at, that is L of cos at is equal to s by s square plus a square if s greater than 0. Again, by using the definition and replace f of t is equal to cos at here, and then we use the same formula. Here we replace a is equal to minus s and b is equal to a, and then x is equal to t, and then apply the limits. We will get s by s square plus a square if s greater than 0. And next, the properties of Laplace transformation. The properties of Laplace transformation allow engineers to simplify operations, solve equations, and model systems. These properties include linearity, shifting, scaling, and etc. Below is the detailed explanation of the most significant properties. The first one is linearity property. This property states that the transformation of a linear combination of two functions is the linear combination of their individual transforms. Mathematically, it can be expressed as L of f1 of t plus f2 of t is equal to L of f1 of t plus L of f2 of t, and L of c into constant into f of t is equal to c into L of f of t. This property simplifies complex expressions by breaking them down into smaller components that can be transformed individually. Let's see the proof of this linearity property. If f1 of t and f2 of t are two functions of t defined for positive values of t, and if c is a constant, then we have L of f1 of t plus f2 of t is equal to, by the definition. So by the definition, we know that integral of f of t is equal to integral 0 to infinity e power minus st into f of t into dt. So this f of t is replaced by f1 of t plus f2 of t in the definition. And then this function can be multiplied with the e power minus st, so that we have integral 0 to infinity e power minus st into f1 of t dt plus integral 0 to infinity e power minus st into f2 of t dt. Again, this is of the form L of f of t, but the function is f1 of t. Here the function is f2 of t. This is of the form integral 0 to infinity e power minus st into f of t dt. Therefore, we write this as L of f1 of t and this term as L of f2 of t. So, therefore, L of f1 of t plus f2 of t is equal to L of f1 of t plus L of f2 of t. And L of c into f of t is, so here by in the definition we replace f of t is equal to c into f of t. C can be taken outside because it is a constant, c into 0 to infinity e power minus st into f of t dt. This is a our L of f of t, so c into L of f of t. Therefore, the linearity property L of f1 of t plus f2 of t is equal to L of f1 of t plus L of f2 of t, and L of c of f of t is equal to c into L of f of t. We have proved. Then next property, Laplace. By using this property, we can find the Laplace transformation of cos hat. So let us see how to find this. By the definition, L of f of t is equal to integral 0 to infinity e power minus st f of t dt. And we know that the hyperbolic function cos hat is equal to e power at plus e power minus at by 2. L of cos hat is equal to L of e power at plus e power minus at by 2. This 2 can be taken outside. So 1 by 2 into L of at plus L of e power at plus L of e power minus at. We can write like this by using the linearity property. Already we know that we have seen this L of e power at. This is 1 by s minus a. Also, this is L of e power at is equal to 1 by s minus a, and L of e power minus at is 1 by s plus a. is substitute here 1 by s minus a for L of e power at and 1 by s plus a for L of e power minus at. This is 1 by 2 into 1 by s minus a plus 1 by s plus a, and then we can cross multiply this s plus a, 1 into s plus a is s plus a plus 1 into s minus a is s minus a divided by s plus s minus a into s plus a, that will be written as a square minus a square, as you know that a plus b into a minus b is equal to a square minus b square. So using this formula we can write s minus a into s plus a is equal to s square minus a square. So here plus a and minus a will get cancelled. S plus a is 2s divided by 2 into s square minus a square. This 2 will get cancelled. Therefore, s by s square minus a square will get for L of cos h a t if s greater than modulus of a. Similarly, we can find the Laplace transformation of sin h at, and the hyperbolic function for sin h at is e power minus at minus e power minus at by 2. Hyperbolic function for sin cos h at is e power at plus e power minus at by 2. Sin h at is e power minus at minus e power minus at by 2. So likewise, L of sin h at is equal to L of e power at minus e power minus at by 2, and 1 by 2 can be taken outside, and then we know L of e power at and L of e power minus at, and substitute the Laplace transformation of these functions, and we can simplify it. So finally we get a by s square minus a square if s greater than modulus of a. By using the linearity property, we can find the Laplace transformation of cos hat and sin hat. So next, shifting property. This shifting property shows that multiplying the finite domain function by an exponential e power at shifts the S domain representation by A units. So if L of f of t is equal to f bar of s, then L of e power minus 18 into f of t is equal to f bar of s plus a. So let us see the proof of this shifting property. L of f of t is equal to, by this is by the definition. L of f of t is equal to del 0 to infinity e power minus st f of t dt, and we replace f of t by e power minus 18 into f of t, which is equal to integral 0 to infinity. The e power minus st is already there. This f of t will be e power minus 18 into f of t dt. And the integral 0 to infinity e power minus st into e power minus 18 into f of t dt. So e power minus st into the product of two exponential functions, e power minus st into e power minus 80, and then we can the powers can be added. So therefore integral 0 to infinity e power minus t can be taken outside. So minus s plus a, I keep this t here, minus s plus a into t f of t dt. Already we know that integral 0 to infinity e power minus st f of t dt is equal to f, f bar of s. That is L of f of t. It is denoted as L of f of t. It is given L of f of t is equal to f bar of s. And then L of e power minus at f of t is equal to, because f of t is e power minus st into f of t dt. So L of e power minus at into f of t is equal to f bar of s plus e. Because integral 0 to infinity e power minus st f of t dt is, can be written as f bar of s. Here, this function, this integral 0 to infinity e power minus s plus a into t f of t dt is e power minus s plus at dt, and here e power minus st. So compare this function. So for this integral, we can write f bar of s, and for this integral, we can write f bar of s plus a. Similarly, we can find L of e power at into f of t is equal to f bar of s minus a. Since L of e power at is for we get e power plus at. After that, we take minus t outside. So it will here the term comes like s minus a. So therefore, when we using the definition L of f of t, so L of e power plus at f of t is equal to f bar of this s is. Next we see uh, change of scale property. If L of f of t is equal to f bar of s, then L of f of a t is equal to 1 by a into f bar of s by a. The change of scale property in Laplace transform states that scaling a function f of t by a factor of a in the domain results in its Laplace transform being scaled by 1 by a and the variable s being replaced by S by A. This helps analyze systems with time scaling, compression, or expansion. Let's see the proof of this property. L of f of t, this is our definition. Here we replace t by at. L of f of t is equal to L of f of at is equal to 0 to infinity e power minus st f of at dt. We put a is t is equal to u and t is equal to u by a and find the derivative dt is equal to du by a and a from this a into dt is equal to du and substitute this thing in the integral. So L of f of a t is equal to integral 0 to infinity e power minus s into t is u by a. So u by a t f of at is u and dt is du by a and substitute all those things substituted. So therefore it is equal to this a 1 by a can be taken outside. There is 0 to infinity e power minus su by a f of u du. So this is of the form integral 0 to infinity e power minus st into f of t dt and the variable is the coefficient of the variable u is minus s by a minus s by a and this is given L of f of t, L of f of t is equal to f bar of s. That is integral 0 to infinity e power minus st into f of t dt. If it is like this, we can write f bar of s. Here we have e power minus s by a into u f of u du. Then we can write f bar of s by a. Already 1 by a is outside, so 1 by a into f bar of s by a. This is the change of scale property. Next we see the Laplace transform of derivative. Differentiation property, this is also called the differentiation property of Laplace transform. It converts differentiation in the time domain into multiplication in the S domain. This property is particularly useful in solving differential equations. We see the proof of this property. L of the differentiation property is L of f of t is equal to, it is given f bar of s, then L of f dash of the first derivative of the function f dash of t is equal to the Laplace transformation of the first derivative of the function f dash of t is s into f bar of s minus f of 0. F double dash of t is equal to s squared into f bar of s minus s into f of 0 minus f dash of 0. Let us see the proof. L of f of t is equal to 0 to integral 0 to infinity e power minus st f of t dt by the definition. F of t is replaced by f dash of t as we find the f dash of Laplace transform of the function f dash of t. So replace f of t by f dash of t, which is equal to integral 0 to infinity e power minus st f dash of t dt and the product of two functions So we use the integration by parts. Integral u dv is equal to uv minus integral v du. Let us take from this integrand u is equal to e power minus st, and the remaining part dv is equal to f dash of t dt. And then find the derivative of this function u is equal to e power minus st with respect to t. We have du is equal to e power minus st in the differentiation. The coefficient of t is in the product. So e power minus st, the coefficient of t is minus s, that is in the product minus s into dt. And then integrating this function, so we get the integration and differentiation will get cancelled. We have v, and then this is again integration and differentiation will be cancelled, and we get f of t. V is equal to f of t. Using this integration by parts and substitute here, u is e power minus st and v is f of t. The limits from 0 to infinity minus integral 0 to infinity v is f of t, du is e power minus st into minus s dt. And apply the limits. Applying the upper limit, so e power minus infinity f of t, e power minus infinity we know it is 0, so 0 for the upper limit, and when we substitute the lower limit 0, it is e power 0 is 1 into f of 0 minus upper limit minus lower limit, so that minus sign will come here. So minus f of 0 plus s can be taken outside because the variable we are integrating with respect to t only, so s can be taken outside. So s into integral 0 to infinity f of t e power minus st dt. Again it is nothing but f bar of s, it is given. That is L of f of t. L of f of t is integral 0 to infinity f of t into e power minus st dt. And then we can write this integral is f bar of s. So s into f bar of s here minus f of 0. Therefore, L of f dash of t is equal to just rewrite this equation s into f bar of s minus f of 0. So the one is proved. The another one is L of f double dash of t is equal to s squared into f bar of s minus s into f of 0 minus f dash of 0. Likewise, we can prove this second part is also L of f double dash of t is equal to integral, by the definition, L of f of t, L of f of t is equal to integral 0 to infinity e power minus st into f of t dt, and we replace f dash of t. F of t is f double dash of t because we are finding the Laplace transform of the second derivative of the function f of t. So L of f double dash of t is equal to integral 0 to infinity e power minus st f double dash of t dt. Then u is equal to the integration. By using the integration by parts, we have to find all those things. So let us take u is equal to e power minus st and find the derivative. Du is equal to e power minus st into minus s dt, and dv is equal to f double dash of t into dt, and find integrating this function, we get v is equal to f dash of t. And we substitute here, it is u v minus integral v du e power minus st into minus s into dt. By applying the integration by parts, we get e power uv, the limits from 0 to infinity, minus integral v du. Here we have substitute, and then upper limit, when we apply the upper limit, it will get 0, and the lower limit, it will be minus f dash of 0 plus means this minus s can be taken outside, plus yes, we will get integral 0 to infinity f dash of t into e power minus st dt. Already we know that L of f dash of t is equal to s into f bar of s minus f of 0 minus f of 0 plus, for this integral we replace s into f dash of f bar of s minus f of 0. Already s is here in the outside, s into this integral is s into f bar of s minus f of 0, and then s into s into s is s square f bar of s minus s into f of 0 and minus f dash of 0 here. So therefore we have proved L of f double dash of t is equal to s squared into f bar of s minus s into f of 0 minus f dash of 0. This is the Laplace transform of the derivative. And then next we see the Laplace transform of integrals. If L of f of t is equal to f bar of s, then L of integral 0 to infinity f of u du is equal to f bar of s by s. This property converts time domain integration into s domain division. This is essential in system analysis where cumulative effects need to be considered. Let us see the proof of this property. Definition, L of f of t is equal to integral 0 to infinity e power minus st f of t dt. We are finding the Laplace transform of this integral in 0 to infinity f of u du. Let us take this integral as g of t and put t is equal to 0 here. G of 0 is equal to 0 to 0. Integral 0 to 0 f of u du. Both the upper and lower limit are 0. Therefore, the integral is 0, and this function is differentiate with respect to t. We get d by dt of g of t is equal to d by dt of integral 0 to t f of u du. This is f of t by the fundamental theorem of calculus. That is, if f of x is equal to integral x a to x f of t dt, then f dash of x is equal to f of x for every x in the interval. That is d by dx of integral a to x f of t dt, which is equal to f of x. By using this theorem, we have d by dt of g of t, that is g dash of t, which is equal to f of t. Now, taking the Laplace transform Laplace transform on both sides in the equation, in the equation 2, we get L of f of t is equal to L of g dash of t. We know L of f of t is equal to s into f bar of s minus f of 0. So in the previous, the one Laplace transform of derivative, we have discussed this property L of f of t is equal to s into f bar of s minus f of 0. So we apply for g dash of t also here. Therefore, L of f of t is equal to s into g bar of s minus g of 0, and g of 0 is 0. Therefore, s into g bar of s is equal to f bar of s, and this implies g bar of s is equal to f bar of s by s, and g bar of s is L of g of t. Uh, uh, since L of f of t is equal to f bar of s, we can write L of g of t is also g bar of s. Therefore, g bar of s is equal to L of g of t, which is equal to f bar of s by s. What is our g of t? We have taken as g integral 0 to infinity f of u du. Therefore, L of integral 0 to infinity f of u du is equal to f bar of s by s. This is the Laplace transform of integrals. It is integration property. Next, we see the multiplication of t. If L of f of t is equal to f bar of s, then L of t into f of t. The multiplication of t means the function f of t is multiplied by t. So what is the our Laplace transform of this t into f of t? Minus d by ds of f bar of s. Let us see the proof. This is the definition, and this can be written as f bar of s. And differentiating with respect to s on both sides. Differentiating with respect on s on both sides. And differentiation integration are inverse to each other. d by ds of f bar of s is equal to d by ds of integral 0 to infinity e power minus st f of t dt. And here we could see this is the variable with respect to s. Here the integral is with respect to t. Differentiation and integration both are not with respect to the same variable. They are with respect to the different variable. But if the integrand has the variable yes, integrand has the variable yes, we can partially differentiate with respect to yes by Leibniz theorem. Therefore, we can partially differentiate with respect to yes. If the integrand has the variable yes, and it can be written as integral 0 to infinity dou by dou s of e power minus st f of t dt. So we are differentiating, partially differentiating with uh, 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 we are differentiating, we are partially differentiating this function only, dou by dou s of e power minus st. Therefore, integral 0 to infinity e power minus st, differentiating this with respect to uh, s, we have minus t in the product, e power minus st into minus t f of t dt. And minus can be taken outside. So, integral 0 to infinity e power minus st into t into f of t dt. And we know that L of f of t is equal to integral 0 to infinity e power minus st f of t dt. Therefore, compare these two terms and minus sign, and here the function is t into f of t. So instead of f of t, we can write t into f of t. That is d by ds of f bar of s is equal to minus L into f of t. And L of t into f of t is equal to minus d by ds of f bar of s. And then similarly, we can find L of t squared into f of t is equal to minus 1 squared into d squared by ds squared f bar of s. So differentiating 1 with respect to x. What is our 1? This is our 1. Differentiate d by ds of f bar of s is equal to minus integral 0 to infinity e power minus st t into f of t dt is our equation. This equation is differentiated with respect to s. So d squared by ds squared f bar of s is equal to minus d by ds of del 0 to infinity e power minus st into d into f of t dt. And again, this here the variable yes and here the variable t, but in the integrand has the variable yes, then we can partially differentiate this function. So therefore, minus integral 0 to infinity, this can be written as dou by dou s of e power minus st minus uh, t into, sorry, minus, this will not come, t into f of t dt. And then uh, again differentiating this e power minus st with respect to x. So we will get e power, one more term right here, minus integral 0 to infinity e power minus st into minus 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 t into t f of t dt. This is t. T into f of t dt. This minus will get plus, and e power minus st, t into t is t squared and f of t dt. And this is L of t squared f of t. So L of f of t is interval 0 to infinity e power minus st into f of t dt. Here instead of f of t, we have here t squared f of t. Therefore, this can be written as L of t squared into f of t. And therefore, L of t squared f of t is equal to here d squared by ds squared into f bar of s, and here we can write this minus into minus as minus 1 the whole square. Therefore, here also we can write minus 1 square, and therefore L of t squared f of t is equal to minus 1 squared into d squared by ds squared f bar of s. Anyway, minus 1 the whole squared is 1. So instead of that, we can write minus 1 the whole square to generalize this property. So similarly, L of t cube f of t is equal to minus 1 the whole cube d squared by ds squared f bar of s. And in general, L of t power n f of t is equal to minus 1 power n d power n by ds power n fn of s bar. Thank you.